So to complete section 9.1, parametric curves, we have just a few more examples to go through. This next one asks us to show that the ellipse x over a squared plus y over b squared equals 1 is parametrized by the curve c of t equals a cosine t comma b sine t, and for values of t between 0 and 2 pi. So it's actually a pretty straightforward just confirmation really of these two functions or these two definitions representing the same curve. So really all we need to do is it's a bit of a substitution and just checking that things actually work out the way we expect them to. We should note that this is a really common parametrization for an ellipse, or a special case would be a circle. So let's keep that in mind for the future. We'll see somewhat similar parametrizations for circles maybe later on in section 9.2, and certainly you'll see it quite a bit in Calc 3 if you're going on to the next calculus course. They also asked us to graph this for the case a equals 4 and b equals 2. Remember that a and b represent the major and or minor axes. Since a is larger than b in this case, a would be the major axis and b would be the minor axis. I'll leave that to the reader to graph these. Maybe I'll point out what some of these t values correspond to as far as points on the ellipse, but otherwise I'll leave this up to the reader. So to confirm that the Cartesian equation is equivalent to this parametric equation or parametric definition, we take the parametric definition, c of t is a cosine t, b sine t, x is the first component, y is the second component, and we remember that x and y are in this equation, so we plug in for x and y, this substitution for each of those variables. We're dividing a cosine t by a, b sine t by b, squaring each of those things on their own on the outside here. We've got cosine squared t plus sine squared t. That happens to be equal to 1, which is exactly the right-hand side of our given equation. So in other words, we started with this left-hand side of the equation, then we substituted x and y, and then we confirmed that that was in fact equal to the right-hand side. So this is in fact a valid parametrization of the ellipse. So that's the way we would check any parametrization matches up to the Cartesian equation that it involves. You take whatever x's function is, substitute it in for x, or everywhere you see an x, do the same for y and its function, and hopefully you'll arrive at an identity that matches the one that you were given. If not, then either a mistake happened or the curve just simply doesn't represent that, that parameterization doesn't represent that Cartesian curve. Okay, so if a is 4 and b is 2, let's talk about what some of the points on this ellipse are. Well, remember that t equals 0. We're actually thinking about, if we range t from 0 to 2 pi, we're thinking about the unit circle in some sense, right? The unit circle starts at 0, ends at 2 pi. That's the positive x-axis. 0 and 2 pi are the same point, same place. So angles in between would be pi over 6, pi over 3, and pi over 2. So that's here, roughly here. And then the angle pi over 2 is the y-axis. Angle is 0, pi over 6, pi over 3. So these 4 angles, so we should get points in the first quadrant. So that's really all I'm going to point out in this, in terms of, as far as trying to graph this thing. So c of 0 would give us the point 4 times cosine of 0. This is also good practice with this parametric notation, times 2 times, or comma, 2 times sine of 0. Well, cosine of 0 is 1, and sine of 0 is 0, so we have 4 comma 0. That's exactly what we would expect on this ellipse. The major axis is 4, so we should go as far over as 4 in this one. And that means that we should go as far up as 2 on the y-axis. Well, to check that one, this would be the angle pi over 2 up here. So we just plug in c of pi over 2 to confirm that. Do that off to the side here, pi over 2. And you note that cosine of pi over 2 is 0, so you get a 4 times 0. And then sine of pi over 2 is 1, so 2 times 1, and we'd get the point 0, 2. And that's exactly, or more or less, what we were showing right here. Okay, so in between, we'll find some other points, and then we could actually come up with a sketch of the graph of this based on that. Minor axis is the vertical axis, major axis is the horizontal, and we've got at least these 2 points graphed now. I'll let the reader do the rest, or the student do the rest of these, 0, 2, to confirm that that's actually the case. Now these will be a little bit harder to see, the 2 intermediate ones that we've got listed right here, but they should fall approximately where you'd expect them to. Note we could draw the ellipse a little bit better than I have it here, but we're not too worried about that. It's just a sketch. Let's see. Okay, so to really address the sort of the power of these parametric curves and how sort of varied things can get, let's have a look at this example. We've got 3 different parametric curves, C1, C2, and C3. They ask us to compare and contrast the motions of the particles described by each of the following curves. Okay, so each of these curves is describing a trajectory of a particle. So if we eliminate the parameter, in the first case, we have C1 is t cubed comma t to the 6th. If we eliminate t, we end up with a function y equals x squared. Remember that we just said everywhere there's a, well, t would be equal to the cube root of x, and we plug that in for t here. So we have cube root of x to the 6th, and we just get x squared. So that's how that comes about. And that's how it'll come about in all the subsequent parts below. And well, they don't give us any domain with this parametric curve, so we just assume it's all values of t that are, that we can plug in. And we can plug in any value of t, positive or negative, so we'll just assume that that's the case. We'll always assume the widest domain unless otherwise told. So some points on this curve, t values give us these x and y values, and we can start to plot these, but we realize that we're dealing with a quadratic function, y equals x squared. And the only reason we really got this table now is to understand what happens as t increases. So it's very common to label, it's conventional even, to label these curves in the direction of increasing t. So when t is -1, we see that we're at this point -1, 1. When t is 0, we're at the point 0, 0. When t is 1, we're at the point 1, 1, 1. When t is 2, we're at the point 8, 64. That's way up here somewhere. But what we notice is that as we move, as we move along this curve, as t increases, our direction of travel is, well, sort of left to right. It kind of drops down first, and then it goes upward afterward. So the red arrows are indicating our direction of travel on this curve, are increasing t. Okay, so what happens next? We have C2 of t, and that's t squared comma t to the 4th. When we eliminate the parameter here, we've got y equals x squared. Okay, things are a little bit different. We took plus or minus square root of x for t here, and then we plugged in that plus or minus root, but when we took the 4th power, plus or minus fell out. So it looks like we'd have the same y equals x squared that we had above. Well, again, let's go to the table and see what this parametric curve actually produces. Notice that we have an even power of t in both cases. Even though the Cartesian curve is the same, these are even powers of t versus this one has an odd power of t. So negatives find their way through t cubed. However, -1 for t, our x component, is just +1 thanks to that being t squared. So we have 1, 1. So this is a little bit more interesting behavior. Then when we plug in t equals 0, we get 0, 0. Then we've got these points start to look the same as before. 2 is 4, 16. Only, so it's the same exact curve. I should point this out. It is the same exact Cartesian curve, only it's how we travel it that changes. So despite t equals 2 yielding a different xy point component than this one, we're still on the same curve because the point 864 is still on this curve. We could go down a line or wherever we need to get, I guess it would be the square root of 8 is what we would plug in for t, and then we get 864 out of this parametric curve as well, parametric expression. So it's the method of travel that changes, not the curve itself. So what happens, t equals -1, we're here at 1, 1, and then t equals 0, we travel down to 0, 0. So when t is negative, we're traveling downward towards the origin until we get to t equals 0. And then after t equals 0, we come back and hit t equals 1, and then we go further up for t equals 2, which is 4, 16, kind of off the graph there. So we see that we travel down to the origin, then we travel away from the origin as t goes to infinity. So our direction of travel is kind of both ways, and so that's why we've labeled it as we see here. Slightly more interesting behavior than the one above, where we just traveled in one direction. This one's sort of bouncing off the origin and back out into that infinite leg of the parabolic curve. So for C3 of t, we're starting to catch on to what's going on here. We've got cosine of t and then cosine squared of t. X is cosine t. When we eliminate the parameter, we have the same exact Cartesian curve. That's our sort of framework for this. That's the path that we're traveling on. Now, how much of it and in what manner do we travel this curve is the question. So then we resort to a table once again to see how that goes. Let's use some common values for our t values, for our angle values is what we're thinking about. So negative pi over 2, 0, then pi over 2, positive pi, and let's just see what happens with this curve here. So at negative pi, cosine of negative pi is -1. Well, cosine of pi is -1 as well. But anyway, cosine negative pi is -1. Sine of, let's see, we've got cosine squared of negative pi is -1 squared. So we have -1, 1. Okay, so we knew that we would be on that point. As soon as we got x equals -1, we knew that y was -1 squared. So that's a nice way to shortcut maybe that calculation. So when t equals when t equals negative pi over 2, cosine is 0, and it's 0 in both components then. So we have 0, 0 when t equals pi over 2. So that's this point here. And it looks like we're traveling this direction so far. We're increasing t from negative pi to negative pi over 2. This should be a negative pi over 2, but it could also be a positive pi over 2. We'll see that in a moment. When t equals 0, well, we get 1, 1, because cosine 0 is just 1. So we got 1, 1. And then when t equals pi, or positive pi over 2, as we have labeled here, we get the same exact value. So we travel back down to the origin. And then when t equals pi, we're back at this point. So this thing's just oscillating, sort of bouncing back and forth in the trough of this parabolic arc. And that's what it's going to do infinitely. So there's probably the richest behavior out of all three of these examples in this exercise, or the parts in this exercise. But really this should showcase, for one thing, the fact that we can be talking about the same Cartesian curve in all cases, but we can have very different behavior going on. So this really kind of shows the power of that third variable t, that parameter that shows up now, and it allows us to think about not just a fixed curve, but now a fixed curve, one of these Cartesian curves, as a trajectory whose time traveled is t along the xy coordinate plane. So we've got one more example, and that's to see whether or not two particles along a trajectory intersect or collide. Okay, so going along with the last theme, that parametric equations are representing some sort of motion or trajectory of a particle. We're given that C1 and C2 are the trajectories of two separate particles. And we're asked to determine whether or not they intersect and or collide. So if we think about two particles moving around in two-dimensional space, they of course could collide with one another. They could of course intersect paths. And the difference between an intersection and a collision is that the path, so two particles will intersect if they share a common xy value. In other words, there's an xy value in the plane that they both pass through. Now, they don't have to pass through at the same time in order for there to be an intersection. Now, for them to collide, they have to pass through the same point at the same time. So that's our distinction. Intersection is the same point, not the same time. Collision is same point, same time. You can think of it as a traffic intersection. You might intersect the trajectory of another car traveling perpendicular to you once they pass through with a green light, and then you subsequently get a green light and pass through. However, if one of you runs the red light while the other one's coming through with a green light, then you might possibly collide because you'll be in the same point at the same time. So in order to find intersection and collision, here's our check. We let T1 and T2 be sometimes taking on values between negative infinity and infinity, or whatever they tell us the domain of T should be, the domain of these functions should be. In this case, they're saying any T values, any real T values. So we'll leave that open when we try to solve for these. Now we let there be a T1 and we let there be a T2 corresponding to the first particle's trajectory and the second particle's trajectory, respectively. And what we do with this is we plug T1 and T2 into each of those equations. So we rewrite them as follows, and then we set those two equations equal to each other. What we'll do is sort of build a system of equations that's based on this. So if C1 T1 is equal to C2 of T2, then that's telling us that the x components match. So this one is equal to this one. And the y components match. Y1 of T1 is equal to Y2 of T2. And what we really get out of this is a system of equations, like I was saying before, in two different variables, T1 and T2. And that's what we see here. This is x1 of T1, x2 of T2, y1 of T1, y2 of T2. Two different equations, two different unknowns. Now it's not a linear system of equations because there is a power of T that's not 1, okay, or T2 that's not 1. So some of these could be linear equations. So we could be asking about two lines intersecting or colliding, or two trajectories, which are lines that might intersect or collide. But generally, that's not going to be the case. We see here we have a quadratic term in there. So, we can't use general methods for solving linear systems, but we just, we go by substitution method mainly in these, and that should work out in most examples. Maybe there's an elimination technique, which is similar to linear systems, but should be an example of that in the textbook. So if T1 is equal to this, we can use that as a substitution now. T1 is 4 minus 3 T2. So in this equation, where I have a T1, I'll swap it out for 4 minus 3 T2. And that's exactly what's happening here. We're using the substitution technique. 2 times T1 is this highlighted bit, right? And then minus 1 equals T2 squared. That's this whole equation occurring here with the substitution. Now everything's in the variable T2. It looks like it'll give us a quadratic equation, which in fact it does. This is it. Once we collect like terms, collect them all on one side too. Factor this. And then we see that T2 has two values. T2 is -7 or +1. So those are two solutions for T2. What this tells me now is this system has a solution. It has two solutions potentially. So if there's not a T1 corresponding to one of these two times, then there's no type of intersection corresponding to this time for T2. That would be a rarer situation. More commonly, what we would have is this. You might try to solve for T2, and you might realize, or after a substitution like this, that there is no solution. There are no solutions to the resulting equation of a single variable. You'd conclude that there's no intersection, and you're all done. If there's no intersection, there can't be a collision. In our case, we've got T2 as -7 and +1. These are two possible intersection points. Now what we look for is what is T1 when T2 is -7 or when T2 is 1. So when T2 is -7, we go back to our substitution that we used up here. T1 is 4 minus 3 T2. And when we plug T2 equals -7 into this, we get T1 is 25. Since T1 and T2 don't match, they're not equal to each other, as we've listed here, C1 has an intersection. C1 and C2 intersect at whatever point corresponds to T2 equals -7 and T1 equals 25. We'll get there in just a moment. So this is just an intersection, not a collision. T2 is 1 tells us that T1 is 1. That's what we get when we plug this into this equation again. These two times match, so not only do these two parametrizations have the same point on them for T1 equals 1 and T2 equals 1, but they do it at the same time. So they're occupying the same point at the same time, so that these trajectories are colliding for T1 equals 1, which is the same as T2 equals 1. So what points do these occur at? Well, to find that out, you go back to T2 equals -7. You can plug that into the original equation for C2 and determine what that is. And as a check, you can do the same. T1 is 25. So when you plug in 25 to C1, you should get the exact same XY coordinate. And if you do, you see that that is the case. So you've checked and made sure that this is actually their intersection point. And that point turns out to be 25, 49. Comma 49, x value 25, y value 49. So that's the intersection point, and that occurred at T1 is 25 and T2 is -7. Different times, but they do pass through the same xy coordinate. So that's an intersection point on this trajectory, on these trajectories. And at T1, we go back and plug in 1 for, well, either of these curves, and we can check that we get the same point, which is a nice thing to be able to do. But we'll see that we get 1, 1 out of either one of these, plugging in 1 into either one since the times are the same. And that tells us that we have a collision at the point 1, 1 in the plane. Okay, so that's a collision point and an intersection point for two different trajectories. Again, to recap what would happen if there were no intersection or collision points, which is sort of not a great example to do because you don't see how to check collision and intersection, but you would, somewhere along this process, you would run into a point where you just see that there's no solution. Maybe something I could describe here would be a quadratic equation that has no real solution. So say you plugged in the coefficients of this into the quadratic equation, or the quadratic formula, and you got square root of it negative. Well, then you'd be able to conclude, well, there are no solutions to this. If there are no solutions to this T1, T2, equation that you might come up with from these two equations, this system of equations, then you can conclude that there are no intersection points. There are no ways for this to happen because there are no such t values that can handle it. So that's it for 9.2. This is probably the most complicated thing you'll do is collision and intersection points. But in this is it for 9.1. In section 9.2, we'll start doing calculus with parametric curves. So be sure to check out that video.